My name is Stevie Harper-Sassing, and I will be discussing Amdahl's law, Little's law, and benchmarking. Amdahl's law states that if there are improvements made to a system, the overall improvement of the system is directly proportional to how much of the system that improved part makes up. It is used to calculate speed-up time, and is also used as a direct argument against parallel and multi-core processing because it states that if you have a one-core processor that does a task in 4 seconds, ideally if you add another processor, then that task will be done in 2 seconds. But if there is a part of the system that cannot be changed, that cannot be reduced, then that part of the system has a direct limitation to all the improvements being made, and therefore the processing time might not decrease if you add another processor. Little's law is kind of opposed to Amdahl's law, stating that if bytes are being delivered to a system and the system is being overloaded, if you implement parallel and multi-core processing and you add another processor, then the system will be able to more efficiently deal with the bytes that is being delivered to the system. Benchmarking is a technique used to compare your organization with other leading organizations in the field to see where you stack up. But in computer science, spec benchmarking is a process where an application with a clear-cut configuration and workload is run through your computer system and processor to see how well it operates compared to other computer systems.
Hi, my name is Abigail Wallace, and I'll be listing and briefly describing some of the techniques that are used in contemporary processors in order to increase speed with respect to computer design, as well as explaining the concept of balance. So firstly, there's pipelining. This is the continuous movement of instructions through the processor through a pipe with all stages processing at the same time. Then there's branch prediction. This is a technique that involves the processor predicting the way a branch will go based on the next instruction code that will be fetched from memory. Then there's superscalar execution. Superscalar execution is the ability to execute several instructions during a byte cycle with the use of multiple parallel pipelines. Then there's data flow analysis. This is a technique that analyzes the flow of data over time in programs for optimization or debugging. Lastly, there's speculative execution. This is an optimization technique that involves branch prediction as well as data flow analysis, and it allows processors to execute a series of tasks in advance before they appear in the program execution in order to have the information prepared to reduce latency. Performance balance. When some components in a computer design have been improved and others haven't, these components will be unable to keep up. Performance balance is a concept that states that a computer's architecture can be adjusted in order to balance the performance of various components to obtain maximum performance functionality.
The von Neumann bottleneck is a concept where there is a throughput limitation due to the insufficient rate of data transfer between the CPU and memory. This causes the competence of the CPU to be reduced as the CPU remains idle for a period of time while the data is being fetched from memory via the system bus. In my research, I found two proposed solutions: processing in memory and the neuromorphic or brain-inspired computers. Both of these operate by reducing data movement and allowing processing to occur where the data is being stored instead of transferred to a central processor. This can come in handy when dealing with larger data sets and more memory-intensive applications. Processing memory utilizes a small form factor computer within memory, while neuromorphic computers are governed by artificial synapses and neurons, which are in close proximity to each other and are inherently parallel. Though it may seem a bit far-fetched, these designs do exist and they are utilized within the next generation of AI applications.
Hi, my name is Israel Diet, and I'll be speaking on the alternatives of von Neumann architecture. The Harvard architecture has different memory allocations for data and instructions. This allows it to perform both simultaneously and independently, enabling high performance with respect to time. However, because it has different memory allocations, the implementation can be quite robust. The instruction set architecture provides the instruction set in a stack that can be accessed on request. Because the instructions are explicitly listed, code generation is easier. However, the stack needs to be iterated on each command, which makes time proportional to the amount of instructions within the stack. Neuromorphic computing executes operations and carries out data storage logically together in the memory itself. This allows for faster computing of complex operations by minimizing delay while being energy efficient.